Hi everyone, this is Drew Wharton with Nimble Leader, along with my colleague Scott McMartin. Scott is Managing Director with Nimble Leader. He's also Vice President of On-Time Edge. Scott aligns manufacturing execution strategies, connecting the dots between symptoms and root causes of current manufacturing throughput and profit improvement. During our session today, we're going to review drum buffer rope, the engine to high on-time delivery. We will also discuss how this one concept can drive double-digit increases in throughput while at the same time reducing OPEX and inventory. Okay, let's step into our session for today.
Now, Scott, I've heard you reference DBR as the engine to high on-time delivery. That's a pretty bold statement. Why do you say this?
In our previous session, we discussed the merits of the broader TOC continuous improvement framework. Under the TOC umbrella, there are two key principles that make TOC work: drum buffer rope schedule execution and throughput measures. Today, we'll focus on DBR, and I absolutely do believe DBR is the engine of high on-time delivery. We will explore three components: the root causes of delivery performance, the effect of dependency and variability, and the sales and operations disconnect.
Okay, great setup. Now, Scott, I've seen reports that indicate that the average manufacturer's on-time delivery performance in many cases is barely 80%. Can you take a few minutes to explain why so many companies have such poor delivery performance?
Sure. Let's take a look at the internal supply chain, the four walls of a typical manufacturing company. We buy material, we add value based on our true value proposition, and we ship to our customers on the date we committed. Simple, right? Adding value is how we satisfy our target market customers. Take the market for women's dresses, for example. Each one of these companies sells dresses, but their target market customers are quite different. In the case of the Walmart shopper, tens of millions of them, they are looking for price value. In the case of a dress, a $50 dress. The Nordstrom shopper, tens of thousands of them, if not millions, is buying great service value in the form of selection, return policy, and knowledgeable salespeople. They're looking for a $500 dress. And the Versace shopper, possibly thousands of them, is looking for the unique design and materials value of a look to wear on the red carpet at the Oscars, the $5,000 dress. Different target market customers, different market demographics, different value propositions. Things are now getting a little more complicated. Let's now consider the extended supply chain. And let's further consider our firm is a small player engaged with demanding customers and suppliers. And let's further consider that the supply chain would be several links in length. Things just got a whole lot more difficult. But the challenge of the situation is not yet fully described. In addition to the fundamental market issues companies face, they are also challenged by business systems that assume unlimited material and capacity availability, have no provision for dealing with variability, and lack synchronized information flow. To be honest, Drew, I'm amazed the average on-time delivery performance for any company is even close to 80%. And when it is usually accompanied by high inventories, overtime, and outsourcing costs driving poor operating profit.
Wow, that is a great strategic overview, Scott. A bit complex, so let's see if we can peel back the onion. So in our prior conversations, you have mentioned dependency and variability as facts of life in a manufacturing setting. Now, what exactly do you mean here?
Okay, so here we have a theoretical example of a typical routing. A finished good C made by combining two subassemblies, A and B. As we see, the finished good is created by transforming two raw materials through a repeatable progression of 8 discrete production steps. Not only do these steps have to occur in the order shown, but each step can vary in terms of time it takes, faster or slower than the demonstrated or average time. No operation ever starts or stops when planned, and none of them ever operate at the average speed. In this example, the market demand is 60 units per period. There are 8 steps in this routing through the work centers of varied capacity, ranging from 50 units per period to 120 units per period. I'd like to pose a question to our attendees. What is the throughput of this system? It should be pretty clear that throughput of this system is 50 units per period. The capacity of work center 6, the forging operation. Makes sense, right?
So yes, it does. And so what I hear you saying is the forging operation is the constraint at 50 units, so it actually governs the throughput for the entire system.
Correct.
Okay, Scott. So given we have awareness on the constraint, let's touch on how most companies manage capacity. This graphic does a pretty good job of representing how ugly the sales operations disconnect might become. Can you explain for the group what is going on here and why it matters?
Yes, ugly is a good adjective. This image depicts what is current reality for most discrete manufacturers. Here's a representation of the production schedule looks if we were to peer into the typical ERP planning engine to see what is going on in the forging work center that we referenced earlier. I call it the March of the T-Rexes, partly because of the way it looks, but mainly because the thinking causing this is prehistoric. In most manufacturing companies, orders are happily accepted based on the quotation of the firm's standard lead time, say 4 to 6 weeks, or simply saying yes to any requested date to win the business, then throwing the orders over the wall to production without regard for the true capacity of the organization. Now, here you see these green blocks represent essentially work orders that are to be produced in the forging work center if they're going to be delivered on time. In this case, we have orders that to be completed on time when we committed them would have to be processed by 20 machines in this work center, when the true capacity is only 4 machines. Guess what must happen? Orders must be prioritized. But by what means is this accomplished? The most loudly screaming customer, the latest order, the largest order, the most profitable order or customer? This is the scenario on which many companies operate. They are constantly grappling with how to allocate overbooked capacity.
Okay, so again, significant complexity, and you've set up the problem. So how does DBR address the problem?
Okay, so there are essentially 3 components of DBR. The drum is the system's constraint. Let's set the pace of production. It dictates the throughput of the system. It may not actually be a bottleneck, that is a work center that operates at or below the market demand, but it is a capacity constrained resource relative to the resources around it. Regardless of its true nature, it should be considered a flow control point. The next element is the buffer. It is the means by which a system absorbs the typical process variability. Workers not showing up for work, machines going down unexpectedly, bad material, bad weather, and very typically customers changing their mind about quantities and delivery dates. The rope is essentially the communication mechanism for preventing the overcommitment of the drum resource and the synchronization of the material flow from suppliers into the production system through the drum and then on to the customer.
Okay, Scott, so thanks for the setup. So let's move on to application. How does a real company apply the DBR approach?
Okay, so here is a representation of a real ready-to-assemble furniture manufacturer that we worked with several years ago. In this particular case, the material flow is exactly like that of the conceptual model we saw earlier. We have identified the shape operation in red as the constraint. And this company has several target market segments it serves, not just one. We must now protect the shape work center from being starved of good parts to process. We do this by inserting time buffers to protect the drum and also at material receipt, the final assembly leg before shipping, as well as the shipping buffer to ensure on-time delivery of make-to-order product. We are also employing a stock buffer to ensure we have proper finished good levels to serve online customer and distributor demand who expect overnight shipment. Key is the ability to avoid overcommitting the system constraint, like we saw earlier. So the due date quotation process, represented by the rope, is simultaneously testing capacity and material availability. We don't want to overbook our constraint. So now that we have a means by which we can link demand to capacity, we close the communications loop by adding a rope to signal material release. We only want material to flow into the system at the pace of the drum that we have now properly committed.
Okay, great, Scott. Thanks for the walkthrough there. Now, Scott, I understand there are many different flow variations within manufacturing plants. Does this matter when discussing the merits of DBR?
It does, to the extent that everybody thinks they're a little bit different. The production example I use today is referred to as an A plant from a material flow perspective. In an A plant, purchased and manufacturing components are combined at various points along the way to create a finished good. In a V plant, possibly a steel mill, for example, it is the opposite. A single raw material is progressively transformed into a variety of finished goods at every routing step. A T plant, possibly a configure-to-order computer maker like Dell Computer, makes multiple standard components, which are packaged to customer specifications. In an I plant, it is simply a case of transforming a product through several steps in a straight line no convergence or divergence. All of these material flows, no matter how complex, are characterized by dependency and variability. They have constraints to flow and are supported by DBR to achieve high on-time delivery.
Okay, Scott, so thanks for this overview. So what I hear you saying is that every node, regardless of the plant configuration, can be a constraint, which then impacts the level of material and labor for every other node.
Correct.
Now, if we shift to application, is there one thing that a company can do right now to benefit from the insights you have provided about drum buffer rope? If so, what would you recommend?
Sure. In the last session, we ended with the suggestion to work on identifying the constraint to flow. Now we're at a point where we can talk about how to protect or buffer the constraint against variability. I invite you to connect with me via video conference or possibly a meeting in your plant to develop an initial buffer strategy to improve the flow of your fulfillment mechanism.
Okay, so thanks, Scott. A practical, no-cost offer.
Okay, everyone, this brings us to the end of our time today. If you have questions, please feel free to reach out to Scott or myself. And if we have your email address, we'll be happy to send you a copy of today's slides. In our next briefing on balanced manufacturing flow, we will discuss throughput measures, the high-octane fuel to manufacturing value creation. You don't want to miss that session. And finally, if you're interested in balanced manufacturing flow for your operations, please note we're happy to engage you in a no-cost consultation to begin scoping the performance improvement and savings for your business. Thanks for joining us. We hope you have a great rest of your day.